Hello friends, welcome to Risingpearl.com. Today we are talking about series 13 where we are learning a great deal on surface areas and volumes. This is webisode number 13 and today we are going to continue to look at how do we solve questions on surface areas of combination of solid figures. This is part 4. So friends, now let's talk about the strategy that is involved in solving such questions. So it's a three-step strategy. First step is we try and visualize in our mind which simple solid figures make up our given complex shape in the question. By simple solid figures, we mean the cuboids, cubes, cylinders, cones, spheres, hemispheres, etc. What combination, which all of these simple solids make up our given complex solid figure? First step is this. Second step is now we find out which areas we actually need to add and or which areas we actually need to subtract to get our required area which is being asked in the question. And finally, third and final step is we actually compute these individual areas because we know the formula for total surface area and curved surface area of these simple solids. So we find out these areas of individual solid figures, and using step 2 we find out which areas we should add and which we should subtract to get to our required area. Now friends, let's put this to test. Let's put our strategy to test and solve some more questions. So this is question number 5. Question number 5 is because this is the fourth part of our this mini series where we are looking how to solve such questions. So the question goes like this. A hemispherical depression is cut out from one face of a cubical wooden block such that the diameter L of the hemisphere is equal to the edge of the cube. Determine the surface area of the remaining solid. So first let's visualize the actual wooden solid block. So it will look something like this, and here you will see I have put actually two figures. So the first one, this is the actual wooden block. So our wooden block is a cubical wooden block. So what we have done, we have drawn a cube. Now this is a cube. So each side, let's say it measures A units. So this is the height, this is the length, and this is the width. So they are all A units. And this is the hemispherical depression. So we start out with a full wooden block, right? A cubical wooden block. And then a hemispherical depression is cut out from one face of the cubical wooden block. So we assume, let's say, so a cube has 6 faces, so that from the top face we actually cut out a hemispherical chunk, and depression simply means that it is cut out, it is going inside the cube and not something which is going outside on top of the cube. So a hemispherical depression, almost like a shape of a bowl, which is cut out, this wooden chunk is cut out from the wooden cubical block, right? But what is given is that it is being done in such a way that the diameter L of the hemisphere is equal to the edge of the cube, and that is why the top the figure comes in. So imagine if you are looking at this from the top. So if you are looking at this from the top, it will look something like this. It will look something like this. So the top face of the cube will look like a square, and this is the hemispherical depression which is cut out, that will look like a circle. And now what we know about this hemispherical depression is that if you draw the diameter, right, so we know that this is the diameter. So if the radius is r, so we know that r plus r, which is the diameter of the base circle of the hemisphere, now that actually is equal to L. That is what is given to us, L. Or 2r is equal to L, or r is simply L by 2. But what is also given is that this L is equal to this length A, because that is what this sentence means, such that the diameter L of the hemisphere is equal to the edge of the cube. What this means is the length of the diameter is such that it is equal to the edge of the cube or is equal to one of the sides. of the cube or the top square, and we know that for a cube all sides have equal dimension. So in other words, what is also given is that A, which is the side of the cube, that actually is equal to L. So we know that the radius is L by 2, and we know that each of these sides, they measure L. So with that said, now let's find out how do we solve this question, right? So what is that which is being asked? Determine the surface area of the remaining solid. So the surface area of the remaining solid is, we start out by looking at surface area of the 5 faces of the cube. Remember, whenever we think about surface area, we think, okay, what is the area on which we have to apply paint? So if you were to paint this in a certain color, maybe red, maybe blue, maybe green, what is the area on which I have to apply the paint, or which area do I need to paint? If you think that way, just sometimes it helps you visualize. So obviously I have to paint the front of the cube, the back of the cube, the left side of the cube, the right side of the cube, and the bottom of the cube, right? So surface area of the 5 faces, these are the 5 faces of the cube. So front, back, left, right, and bottom, 5 faces of the cube, plus I have to actually paint the curved surface area of the hemisphere, because the hemisphere, it is in the shape of a bowl, right? So I have to actually apply paint throughout, all around the curved surface area of the hemisphere. So I have to, so the total surface area will be the surface area of the 5 faces of the cube plus the curved surface area of the hemisphere. Now we are left with the top part. Now on the top part, what is that where we have to apply the paint? Very clearly, this part which is highlighted in blue that I am shading right now is the only part which is left, because this part which is empty, it has actually been hollowed out, it has been curved out, there is nothing there. So I have to really apply the paint on this remaining part as shown in this shade. So plus the top surface area, or the surface area of the top face of the cube, which is the 6th side, 6th face, minus the area of the circle, top of the hemisphere. So that is what we have to subtract. Again, going back to the second step of our 3-step strategy. So we find out all areas that we need to actually add and or subtract to get to our required area. So because we are carving out this part, so the 5 faces, the front, back, left, right, and the bottom, we are good with that. So surface area for the 5 faces of the cube plus the curved surface area of the hemisphere, very important because we have to apply paint throughout the curved surface area of the wooden block, plus this little part which is going to be left over on the top face of the cube. So in this square we have this part which is left and the remaining is hollowed out or taken out. So how do we find out this? So we find out the total surface area of the square and the top, and then we subtract this area of the circle. Now that we understand exactly what we need to do, we can actually get on with how do we find it. So surface area, so now we know that cube, if this is A, if this is A, and if this is A, so area will be simply A square. So because we have 5 faces, so total surface area for 5 faces will be simply equal to 5A square. Now we just saw that A is equal to L, right? Because this is A, but this is also the diameter, which is L. So we will say that this is 5L square. So surface area of the 5 faces is 5L square. Similarly, let's move on. Now what about the curved surface area of the hemisphere, right? So simply we know that total surface area of a hemisphere is half 4r square, right? 4 pi r square, right? Or in other words, this will be, this and this will cancel out, it is 2 pi r square, or equal to, let's write this, 2 pi r we know is L by 2 square, or which will be equal to, you will see this as pi L square. You have 2 over here, 2 pi L square, and 4 over here, which will be pi L square by 2. 2 ones are 2, 2 twos are 4. So pi L square by 2. Curved surface area of the hemisphere is pi L square by 2. Now let's continue to move on. Now the surface area of the top face of the cube, which is basically a square. So if this side is A, this side is A, so it will be simply A square, but we know A is equal to L, so it will be L square because A is equal to L. So this will be the top surface area of the top face of the cube, and the last thing which is remaining is the area of this circle. So if the radius is r, we know area of any circle with radius r is pi r square, or this will be equal to pi, r is nothing but L by 2. So pi r square will be equal to this, or it will be pi L square by 4. So friends, now we have calculated each of the 4 areas. So now going back to the total surface area. Total surface area now will be nothing but it will be equal to, we have found out each one of them separately, right? So the first one, surface area of 5 faces, this is 5L square, plus what is the surface, curved surface area of the hemisphere? We found that to be pi L square by, I believe it was 2, pi L square by 2. Then we found, so which was the curved surface area of the hemisphere. Let's just quickly maybe check on that. I am pretty sure that is what it was. So let's take a look. So the top surface, this was that, and yeah, it was pi L square by 2. So now coming back, so what we have is pi L square by 2, and then plus top surface, surface area of the top of the cube was L square, plus we just saw area of the circle was pi L square by 4. So if you just simply add them, you will find out the area in terms of L square. So you will find something times L square, and that will be your answer. So now I will leave the actual computation onto you, and I am absolutely sure you're all very smart and you can find out how to solve this. So friends, so this is how you solve such questions. So I wanted to just do a quick compare to the last question that we saw in the last webisode. So that question was something like this: a cubical block of side 14 centimeter is surmounted by a hemisphere. So what is the greatest diameter the hemisphere can have, and find the surface area of the solid? We actually solved this question in the last webisode, and it exactly looked like this. So we actually had a cube. Instead of the depression, instead of this being cut out like this as we just saw in the last question, it was actually on top of the cube. So the hemisphere, this is the hemisphere which was sitting on top of the cubical wooden block. The point I'm trying to make is, the way, if you go back to that webisode, you will see that the total surface area of the solid in that question as well was, we did the 5 sides of the cube, the front, back, left, right, and the bottom, plus we added the curved surface area of the hemisphere, plus we actually had to add this area. So The point being, whether we are actually carving out a hemisphere or putting a hemisphere on top, the total surface area is same in both cases. Now let's see if we have time for one other quick question. Maybe I'll just talk about how to answer the question than actually solving it for you. A medical capsule, a medicine capsule, is in a shape of a cylinder with two hemispheres stuck to each of these ends. So obviously this resembles any capsule, any tablet that we take. Right? So imagine a capsule. So we have a cylindrical part. So this is the cylindrical part. Let me see if I can actually highlight it clearly. This is a cylindrical part. And then we have two hemispheres. So this is a hemisphere, this is a hemisphere at two ends of the cylinder. Right? The length of the entire capsule is 14 millimeters and the diameter of the capsule is 5 millimeters. Find the surface area. Find the surface area. So let's see if we can actually draw this like this, right? So the total length, what is given is the length of the entire capsule is 14 millimeters. That means starting from this end here through this end here, this entire length, that is from here to here, this is 14 millimeter, right? And the diameter of the capsule, which is this entire diameter, this length is given as 5 millimeters. This is 5 millimeters. So what we have to find out is the entire surface area. So friends, what is important to note is, so for a cylinder, the two important dimensions that we really need, they are the radius and the height of the cylinder. So the radius is given as 5 by 2 because 5 is the diameter, right, of the capsule. So the radius will be equal to diameter by 2, or it will be 2.5. So we know the radius. We know the radius. And what is the height? The height from here to here is given, right? So now, but we know that the radius, that is, this is the radius, r. So r we know is 2.5. That means this length is 2.5 millimeter. So similarly, this length is 2.5 millimeter. So if this is 2.5, this is 2.5, that means combined is 5. So if we subtract 5 from 14, we will be left with 9. So the height of the cylinder, which is from here to here, is 9 millimeter. So we know the height. So we can find out everything that we need for the cylinder or right circular cylinder. And the most important thing that we need for a hemisphere is the radius r, which is also given as 2.5. So we can absolutely calculate the surface area. Let's just write the surface area of the capsule. The surface area of the capsule, and that will be equal to, as we can see from the shape, it will be curved surface area of the cylinder, right, plus 2 curved surface areas of the hemisphere. So this is very important to understand that the surface area, I am abbreviating that as SA, of the capsule that we need to find out is the curved surface area of the cylinder, right? The curved surface area, abbreviated in the abbreviation form written as CSA, of the cylinder, plus the curved surface area of this hemisphere and the curved surface area of this hemisphere, because both are same. So 2 times the curved surface area of a hemisphere. So simply by plugging in the formula, you know the values of r and h. This is h equals this, r equals this. So we know the curved surface area of a hemisphere, of a cylinder, is 2 pi r h plus So, and curved surface area of a hemisphere is 2 pi r square, and there are two of them, so it is twice this, so it will be 2 times this. So by simply putting the values and solving this, you can find out what is the total surface area of our capsule.